Hello, this is Dr. Viv. What we're going to do here is talk about the impulse-momentum relationship, sometimes called the impulse-momentum theorem. The story starts with the real Newton's second law. Now, what do I mean by that? We all know that F equals ma is Newton's second law. Well, the problem is Newton never wrote that. Newton was a clever man, and he knew that the real way to write his second law would be this. The external force, or rather the sum of all the external forces, which I'm going to simply represent as Fext, is dp by dt, or the rate of change of some quantity, which he called the quantity of motion, but today we call the momentum. So the momentum P is given by mass times velocity. So you may have heard of the statement that the 18-wheeler moving at 60 miles an hour has a lot of momentum compared to a car moving at the same speed, and the origin of that statement is that the 18-wheeler has got much more mass than the car, so it's much harder to stop. So the units of momentum come from the units of Newton's second law, and it's going to be newtons times seconds. All right, now this is a very interesting equation. You may wonder how it's related to F equals ma, and it's related as follows. All we have to do is stick this definition in there and find out what happens. So Fx is going to be d by dt mv, and by the usual rules of calculus, this is a product of two functions, so I'm going to get dm by dt times v plus m times dv by dt. So that's the most general equation, and for example, this equation is very important for things like rockets, because for rockets, the rate of change of mass is actually the main source of the rocket's propulsion. The rocket keeps losing mass by burning fuel, or if it's a toy rocket, you jettison something like air or water, and then the rocket moves in the other direction. So if you think of animals like squids, they do the same thing. They put out some water in one direction and they move in the other direction. So that all this is very important. So dm by dt is a very important term. But for things like bridges and things like that, the rate of change of mass is close to zero. So we can write this as ma. So that our usual second law, the form of Newton's second law that we have used before, comes as a limiting case of the general Newton's second law. And the general Newton's second law is what Newton himself wrote, because being a clever man, he did not write a wrong statement. So what we can now do, looking at this, is multiply both sides by dt, or take the differentials as they would say in calculus. So I'm going to get fx times dt is equal to dp, and now I'm integrating both sides from some initial to some final time. I'll just call it I and f. So that's an interesting statement, because by the fundamental theorem of calculus, the integral of a differential is just the change. So this gives us the impulse momentum theorem. This integral is called the impulse integral jx. So fx integrated over time is just the impulse. So I'm going to get the external impulse, or the sum of the external impulses in a more general case, which is jx, is going to be the change in the momentum, delta p. And that statement, that the external impulse is a change in the momentum, is known as the impulse momentum theorem. So for the rest of this video, we'll talk about applications of this. By the way, the one thing to note is momentum is a vector. It gets its vector characteristics from velocity. So the change in momentum also is a vector. So we should be careful about things like that. One of the best applications of the impulse momentum theorem is finding the average force. So if you look at a real life process, such as a baseball game, when the batsman hits the ball, when the batter hits the ball, then you're going to have a very complicated looking force. Okay, there's some initial time Ti and some final time Tf, and this is usually called the collision time, delta T, COLL, call. And so there's going to be a complicated force profile. These days, with intelligent chips embedded in bats, you can actually find these force profiles and you can analyze them on the computer and design better bats and better players, I guess. But what we can get from this using the Lagrangian mean value theorem is that there is a concept of an average force. The average force is a rectangle such that it has the same area as the main thing. So we'll call that F average. By the mean value theorem of Lagrange, it's guaranteed to exist. So we can write the next net impulse as simply the average force times collision time. So that's a great application. You can find the average force by finding the change in momentum and dividing it by the collision time. Change in momentum is rather easy to find. So let's look at an example. Let's continue the baseball example. You have a baseball bat and it hits a ball. So the baseball is coming here with a speed v0 or velocity v0, I should say, and it's going to get hit by the baseball and then bat, and then it's going to move in this direction, let's say, with some final velocity vf. I'll call this angle theta, and let me choose my axes to be positive x here and positive y there. So I would like to find the average force on the, just to make sure everybody understands this, the baseball bat. And I'm going to find out the average force in this problem. So using the definition, or using the real Newton's second law and the impulse momentum theorem, we can write F average is going to be the rate of change of the change in momentum over the change in time. So you can see it's almost like the calculus approximation of dfx equals dp by dt, except it's written in terms of averages. So that's going to be mass times the final velocity minus the initial velocity divided by delta t collision. The final velocity is given by the x component is vf cosine theta. The y component is vf sine theta. Keep in mind that left is positive and up is positive. And the initial velocity, because left is positive, right is actually negative, is going to be negative v0, and the y component is 0. I'm denoting vectors as ordered pairs to avoid writing I hat and j hat. Delta t collision. And that's really your answer. There's nothing more I can do with this except maybe combine the x terms together and the y terms together. So let me just do that. I get vf cosine theta plus v0, because of the two minuses becoming plus, comma vf sine theta divided by delta t collision. In a real problem, you'll be given vf and v0 and m and delta t call, so you can figure out the average force. So that's a simple example. I'll call that example 1. This business can also be applied to systems. So when you apply to systems, you are, instead of writing initial momentum and final momentum, you write sum of the initial momentum and sum of the final momentum. So let's write this impulse momentum theorem for systems. I'm going to get jx vector is equal to the sum of the changes in the momenta of all the objects in the system. Now a special interesting thing happens when the external impulses are 0. So if jx is equal to 0, sometimes this only applies in the horizontal direction or the vertical direction, but in general, if jx is equal to 0, then I'm going to get the sum of the momenta final is equal to the sum of the momenta initial. This is sometimes called the conservation of linear momentum. So we have learned two conservation laws so far, the conservation of total mechanical energy and the conservation of linear momentum. Later on, we'll learn about the conservation of angular momentum. Let's take a simple example of this problem. So example 2 is really this. You have a mass m, let's say a clay ball, that's thrown against a block, which is initially sitting, minding its own business, on a smooth floor, let's say. I like to indicate before and after with a dividing screen. So this is before, and that's after. You should think of the collision time as happening there. So afterwards, the clay ball sticks to the block and sends it scooting on the floor. What's the final speed? And if there's any energy lost in the collision, what is it? So let's solve this problem. The system initial momentum is just going to be that of m, little m. So I'm going to get m times v naught. And at the end, both of them are moving together. So I'm going to get m plus m times v. So immediately we can solve for the unknown speed, final speed. It's just m over m plus m v naught. Now if you want to be careful, you'll put the velocity vectors, but since this whole thing is happening in one dimension, I'll dispense with that. Now to answer the kinetic energy question, we just have to calculate the kinetic energy after, before, and then compare. So let's do that. K final is 1/2 m plus m v squared, because the total mass has to be considered. The capital V is known to us, so let's substitute. So I'm going to get m squared over m plus m squared times v naught squared. Now one of these m plus m factors cancels out, and so the answer is going to be 1/2 m squared over m plus m v naught squared. Then we can calculate the percentage loss of kinetic energy by computing this ratio, kf minus ki divided by ki. So ki is just 1/2 little mv squared. I'll notice that I have 1/2 little mv squared here. So I'll take 1/2 little mv squared v naught squared common, and then I'm left from this term, I have m over m plus m minus 1 divided by 1/2 m v naught squared. So these two cancel out, and this is just negative. That's little m. So let me just do this. Little m minus capital M minus little m over m plus m. Little m cancels out, and that's negative capital M over m plus m. So you notice that actually most of the energy is lost, because capital M, if it's bigger than little m, let's say you have a bug hitting a windshield of a truck, most of the energy is actually lost, and the truck barely moves, because little m divided by the total mass, the mass of the bug divided by the mass of the truck plus the bug is such a small quantity that the truck barely moves. But most of the energy is lost. As you can imagine, the bugs get squashed on the windshield. So there's another way to look at the kinetic energy formula. I'll just indicate that briefly to conclude the video. And that is using the fact that the kinetic energy, which is 1/2 mv squared, can also be written as 1/2 m squared v squared over m. What's the point of doing that? Well, the numerator is just p squared over 2m. In fact, for advanced physics, p squared over 2m is the correct way to write momentum. No one ever writes it as 1/2 mv squared. So using this, we can write the kinetic energy final is pf squared over 2 mass final, and the kinetic energy initial is pi squared over 2 mass initial. It's immediately obvious since Pi equals Pf due to momentum conservation, and that final mass is bigger than the initial mass because they stick together, that the final kinetic energy must be less than the initial kinetic energy. So that's another rather neat way to see that energy is lost.